Nodes in the graph represent mathematical operations, while graph edges represent the multi-dimensional data arrays. The flexible architecture allows you to deploy computation to one or more CPU or GPUs.
When I start to care, then I find there is no one there, but I think
Google Brain Team
of you,
within Google Machine
and I know
Intelligence Research
we are
Organization.
something new. We get high and high, crazy blue, like St. Elmo's fire love so sharp. We fly
Awesome.
that it's hard to know just where you're at. Now I know I'm high and high, crazy blue, like St. Elmo's fire love so sharp. We fly that it's hard to know just where you're at. Now I know I'm high and high, crazy blue, like St. Elmo's fire love so sharp. We fly that it's hard to know just where you're at. Now I know I'm high and high, crazy blue, like St. Elmo's fire love so sharp. We fly that it's hard to know just where you're at. Now I know I'm we get high. We get high.
All right. Get started. Is this the page? TensorFlow. It's still developed. Was that just on a different page? TensorFlow. Did they just update the page just now? Getting started. Get started. I think they just Getting started with TensorFlow. Tensors. The central unit of data in TensorFlow is a tensor. Primitive values shaped into an array of any number of dimensions. A tensor's rank is its number of dimensions. It's a rank 1 tensor, yes, get that one. Which is a vector with shape 3. Yes. A rank 2 tensor is a matrix with shape 2 of 3. Right. This is...
I've been held up in this city for a while due to the rain.
Oh, I see. So as soon as it stops
the
raining,
same?
you'll leave.
No. It's a rank
I hope
3
that the
tensor
rain
with a shape
will never stop.
What?
213.
I'll be able to stay here forever.
So there's 2.
That wasn't meant to be a joke.
Not sure why it would say 213 here, but sure. Well, we first need to install the bad boy. Let's go and install that first. TensorFlow core tutorial. I guess I'll just go through these things here. TensorFlow with CPU support only. If it does not have an NVIDIA GPU, you must install this version. Yes. Installing with native pip. No, I don't know. Do I need to? Okay. Is not installed in your PC. Install it now. Okay. Tensor. Well, actually, I could also use this, I think. But yeah, doesn't really matter, I think. Import TensorFlow STF. Cannot remove entries from non-existent file. Alright. Ah, that's the GPU version. Okay. What the hell is that? I don't know how to make. I don't know if that actually. I don't think it should take that long. Oh, there you go. Cool. Was it import TensorFlow STF? Right. Why is that? It's like hello equals TF to constant. Hello then. Sys equals tf.session. Print sys.run. If it outputs the following and installation is successful, you can begin writing TensorFlow programs. If you are new to TensorFlow, see getting started with TensorFlow. Right, so if it's... Is this an error? No, it does print it out, so I'm guessing this is fine. TF Jenkins home workspace release. Okay. We are relying on Stack Overflow to document installation problems. There it is. Okay. Cool. Cool. There we go. This gives Python access to all of TensorFlow's classes, methods, and symbols. Most of the documentation assumes you have already done this. The computational graph. You might think of TensorFlow core programs as consisting of two discrete sections. Building the graph, running the graph. A computational graph is a series of TensorFlow operations arranged into a graph of nodes. Okay. Let's build a simple computational graph. Each node takes 0 or more tensors as input and produces a tensor as an output. One type of node is constant. Like all tensors, it takes no inputs and it outputs the value it stores internally. We can create two floating point tensors, node 1 and node 2, as follows. That's kind of like what I just did, I think. Node 1 is It's also a float, it seems. Oh, that's implicitly converted to a float by that. It is indeed so. Sure. Sounds reasonable. Notice that printing the nodes does not output the value 3 or 4, as you might expect. Instead, they are nodes that, when evaluated, would produce 3 or 4 respectively. To actually evaluate the nodes, we must run the computational graph within a session. A session encapsulates the control and state of TensorFlow runtime. Yes. The following code creates a session object and then invokes its run method to run enough of the computational graph to evaluate node on 1, 2. Huh. By running the computational graph in a session as follows. We need to create a session. Oh my god. I should do this in a notebook. Okay. Alright, and then on that session I can hit the run. And then within that I can say node 1, node 2. Oh. So I can also emit do it like that as well, right? No, I can't. Using tensor as a Python bool is not allowed. Use if t is not none instead of if t. Tensor is defined and use TensorFlow. Sure, man, sure. We can build more complicated computations by combining tensor nodes with operations. Operations are also nodes. For example, we can add our 2 constant nodes and produce a new graph as follows. So node 3 is tf.add. Okay. So that's still just the add. To run it, we need to run from the sys. Need to run the ruin. Let's also ruin it. Run the node. 7. Okay. TensorFlow provides a utility called TensorBoard that can display a picture of the computational graph. Here's a screenshot of showing how TensorBoard visualizes the graph. Okay, sure. As it stands, this graph is not especially interesting because it always produces a constant result. The graph can be parameterized to accept external inputs known as placeholders. A placeholder is a promise to provide a value later. Right. So we can say A equals placeholder. And then the type B is also a placeholder of 32. adder node. Plus provides a shortcut for tf add. So that's also a node. Okay. The preceding 3 lines are a bit like a function or a lambda, in which we define 2 input parameters and then an operation on them. Right. We can evaluate this graph with multiple inputs by using feed_dict parameter to specify tensors that provide concrete values to these placeholders. We can evaluate this graph with multiple inputs by using the feed_dict parameter. Right. To specify tensors that provide concrete values to these placeholders, right? So run. So I'm thinking the session, so the run method has 2 Where you at, man? Well, this is pretty complex for me. I don't know what this is. But in the run method, we placed a single node, and here is like a second parameter, which is then I guess the feed_dict parameter. Okay, sure. Suspend run adder node, and then you pass something into the adder node, which is a dict. An A. So those are these things here. A. A is 3 and B is, for example, 4.5. And I can't change this to C because that will fail because that's not defined. And that's because A is it's a placeholder. That's why. But could I have said adder node is A plus C? Now C is not defined, so you need to provide a placeholder. And then in the feed_dict parameter, you provide the values for the placeholders using a dict. Cool. And apparently here you can also add a array Doesn't really matter what I'm. All right. Awesome. The board looks like so. Adder number, adder node, B and A. Cool. We can make the computational graph more complex by adding another operation. Okay. Add and triple. Adder node times 3. Cool. Brings a sys.run of add and triple. And then you need to provide it the dict again. Triple. So A equals 3, and then B equals 90. And so that would be 93 times 3. Okay. So what's this Y thing here? Y. So Y would be 3 in this case, or what is? In machine learning, we will typically want a model that can take arbitrary inputs, such as the one above. To make the model trainable, we need to be able to modify the graph to get new outputs with the same input. Yes. Variables allow us to add trainable parameters to a graph. They are constructed with the type and an initial value. That's capital W or like some TF dot variable. They have a initial value and they have a type. Okay. TF dot variable. Shouldn't like on tab here. Minus 3. TF dot float 32. And X is another placeholder. And then it says linear model W times X plus B. Modify the graph to get new outputs with the same input. New outputs with the same input. Yeah, so you change like the internals. Variables allow us to add trainable parameters to a graph. They are constructed with a type and initial value. That's the initial value, the type is that, the placeholder. Constants are initialized when you call tf.constant and their value can never change. By contrast, variables are not initialized when you call tf_variable. To initialize all the variables in a TensorFlow program, you must explicitly call a special operations as follows. doesn't have the actual value there. Init equals tf.global variables initializer. And within the session element. So now B is a handle to the TensorFlow subgraph that initializes all the global variables. Right. Since x is a placeholder, we can evaluate the linear model for several values of x simultaneously as follows. So if we can print I hate typing. X can be any one of these. Now it says W, which is 0.3 times 1 plus B, which is a negative number, so that equals 0. It just zeroes out. Right, got it. We've created a model, but we don't know how good it is yet. To evaluate the model and training data, we need a Y placeholder to provide the desired values. We need to write a loss function. A loss function measures how far apart the current model is from the provided data. Yes, we'll use a standard loss model for linear regression, which sums the square roots of the deltas between the current model and the provided data. Linear model minus Y. But why? Creates a vector where each element is a corresponding example's error delta. We call tf.square to square that error, and then we sum all the squared errors. We sum all the squared errors to create a single scalar that extracts the errors of all examples using tf reduce sum. Okay, so y is just a placeholder again. Cool. Squared deltas is the square of a linear model. Now a linear model, okay, so you still need to provide it the parameters, sure, okay, minus y, that's the placeholder I just created. Okay, so that squares every value that's returned, and it gets squared. Sure. The loss is the reduce sum of squared deltas. That's just summing up all the values. Okay. exciting. Let's print it. The loss. And then there's two parameters because we have. But how do you know what the parameters are in this case? Because loss doesn't really take any parameters as such. So it goes all the way back to the square function here. Okay. Let's do 0, 1, 2. And then y equals -1, 0, 1. Produces a loss value. Let's see if we can figure out what it's doing. Linear model. So, oh no, it's pretty much this one here. Let me add those in. So, there's 1, 2, 3, 4, 5, 6. And this is 3, 4, 5. So it's 26 and 5. It's square rooting all of these. I guess. Is it not? I think it is. And then it's summing them up, but I think it sums those up. Sure. We could improve this manually by reassigning the value of W and B to the perfect values, -1 and 1. The variable is initialized to the value provided to TF. But can be changed later using the operations like TF.assign. For example, W equals -1 and B equals 1 are optimal parameters for our model. You can change W and B accordingly, so you need to, that's how you change, you assign them a new value. So do that. Oh. Oh, you have to run them as well? That's something I would have forgotten. And then this is 0. This is 4. Okay. We guessed the perfect value of W and B, but the whole point of machine learning is to find the correct model parameters automatically. Awesome.
I appreciate the sentiment, but I'm afraid it's nothing more than a daydream.
Let's go to bed. We will continue tomorrow.